Okay, hello all. Welcome back to Lecture 5, CE 366 Geotechnical Engineering 1, Lecture 5, Total and Effective Stresses. So in this lecture, the learning objectives are, first, we will learn how to calculate 4 different kinds of stresses. The first one is the vertical total stress. The second one is the vertical effective stress. So both those two are vertical stresses, but the difference is one being total and the other one being effective. The third one is now we look at the horizontal total stress, sigma h, and also the horizontal effective stress. So a couple patterns over here. So we have sigma, where we have sigma in geotechnical engineering. This is the symbol of stresses. So this means stresses. And if this is just sigma, then there will be total stress. And if you come with a pi, so this pi means effective stresses. So effective means, so whenever we use the phase, so effective stress means we are considering the effect of the water. The effect of the water that reacts and also exists within the soil matrix. Oops. So for the case that you only have dry soil, there's no water, so you got to be total stress. There's no effective stress for dry soil. But for saturated soils, you can consider two scenarios. You can consider total stress response or effective stress response. So when we have like a dry soils, there will be like a no water. But if we have so this is dry soil. But if we have a water table there, then now you have saturated soil. In this case, you can consider effective stress, but you also can consider the response as total stress. Versus in dry soil, you gotta be just total stress. So whether you should consider uh, effective stress or total stress analysis, this is come to the topic of more advanced geotechnical engineering. It is more like in the design part when you design of your foundations. So you consider it as a total stress response or effective stress response, or should you take account the effect of the water? So that will be the design problem that geotechnical engineers need to be face every days. So if you want to learn more about the design part of a total stress and effective stress, you need to take the next class, CE 467, Geotechnical Engineering Design 1, which we'll be offering the fourth semester. So we learned this like a total stress and effective stress. We also have the subscript over there, V and H. So V stands for vertical, H stands for horizontals. So with these combinations, effective or totals, verticals or horizontals, with all this two different combination, the two set of combinations, it give you 4 parameters. Uh, the one more time, the vertical total stress, the vertical effective stress, the total horizontal stress, and also the horizontal effective stress. So 4 of them, and we will learn how to calculate all 4 of them. So one more time, it's the verticals and horizontal. What does it mean? Is when you look at a soil, or what if this is your soil profiles at any depth. For example, you have metro tunnels, like the purple line that we are doing now at Los Angeles, the purple line extension project. So for example, you want to design for this tunnel, then if you want to construct this, you need to find out how thick your tunnel liner, how much concrete you put on, right? such that the tunnel structure can withstand the stresses adding along the underground structure. So you need to find out the vertical stress at the crown, and also so the top part of the tunnel we call the crown of the tunnel, and also you want to find out the at the midpoint, which is we call the spring line. So when the tunnel boring machine try to mine through the ground, you will go through the center line, the spring line of the tunnel. So you want to find out the horizontal stress at this point. So you consider horizontal total stress, so you consider horizontal effective stress. So those questions, like for later on studies. But anyways, um, those four parameters there is very important for geotechnical engineers. So pretty much this kind of like every day is like a workout for the engineers. They need to find out all the stresses such that they can design for the geotech structure. So this is a very very important stresses. So if you want to like do well in this class, or at least like maybe my minimum requirements for you to pass this class is for us to able to calculate all the stresses. So you take some practice. Maybe after this lecture you get better, and at the end of semester you should be feeling very comfortable on calculating all these four stresses. So that's objective number one. And the second objective for this lecture is to understand or the concept of soil stress history. So we get to that. So let's start with the most straightforward one. Remember, we have four parameters we need to work on. The first one we look at together will be the total vertical stress. Remember what is total vertical stress? So this is sigma means stress. And total stress means there's a no like apostrophe, no points right there, just a sigma. And vertical stress means like a subscript of V. So we will try to find out the total vertical stress. And theoretically, what does it mean is when you have just an open field, free field conditions, again, free field conditions means like a no structure on top of your soil profile. So this is your soil profile. This is your soil there. There's no like a surcharge, no structure. But if you're on a soil profile that you do have a structure, either like a buildings or a dam, then that means this is not a free field. So now at the free field conditions, at any depth, if you look at a pond of within a soil profiles, and you want to find out the stress at that point, which means that at a certain depth of a given soil profiles, essentially you are trying to the stress at this point, the loading for this point come from is from the soil weight. So these are all the soil weight. Above the inches the pond. So pretty much we are looking at the stresses above the locations you want to, or the depth you want to look at, and the weight come from the self weight or the soil weight or the soil volumes, the mass of the soil volumes above it. So if you want to calculate the stress at this point, pretty much just we try to find out the stress on this soil elements. So if you want to find out the stress, then what we need is we need the soil unit weight. Because once we find out the soil unit weight, go back to lecture one, we talk about the phase relations. So if you know the weight and you know the volumes, what you can do is like go ahead to take a soil samples from the field, and then like from the Shelby tubes, you know the volumes, and then you weight it in the lab with a scale. Then you know the weight, and then you know the volume. Then you can find out the total unit weight. So that's how we find out the unit weight of the soils. And if you know the unit weight and you know the depth, then you can find out the stresses. For examples, we know the soil unit weight for this site is 120 pound per cubic feet, and you want to find out the stress at a depth of 10 feet. So the soil stress becomes the soil unit weight times the depth. So this is 120 pound per cubic feet, and then times 10 feet, and you work out the unit, then it becomes 1200 pound per cubic feet. Sorry, square feet. So now you get the stress. This is the vertical stress at 10 feet. And you realize actually the stress is highly like a depth dependence. So the unit weight can be a constant, but the depth is a variable, depends on which locations you're looking at. So the better way to present your stresses. Oftentimes, like we do this as engineers too, geotech report or design presentations. Instead of like a single numbers that like people need to keep update when the depth change. It's very powerful that we can illustrate with one plot. So what we call this the soil profile or the stress plot, which the x-axis will be the stresses, can be any kind. This time we are looking at the total vertical stress, the most easiest one. And then like the y-axis will be flipped over because in our geotech world, uh, we go down with the depth. So we kind of like upside down the polarity. So when you keep going down, there will be more positive. So the y-axis is the flip of the depth, and then now what we know is the stress at the ground surface is 0, and the stress at the depth of 10 feet that we just calculate together is 120. Sorry, 1200 pound per feet square. So this is one. So this is over here. So this is 1200. And realize the equations that we have. This is everything is increased linearly with the slope of the unit weight, because we know the simple equations, how we find out the stress. So this is how we present our stress with a simple figure, what we call the stress plot. So the math is easy, simple equations, but the expectations of this class is for you to able to present or to illustrate how the stress change with depth, which means the expectations for you in exams and homework is you're able to come up with the stress plot. Okay, as we know, in the real world, the ground is not just homogeneous soils. Instead, what real soil is layers after layers. So more realistic is something like this on this slide. You have different soil layers to composite the soil profile. For example, here we have 3 different soil layers with 3 different soil unit weights. So now the question is like how to calculate the vertical total stress based on different soil layers. And again, like we are not just like happy with like a simple calculations to finish at like a particular stress that you want. And as an engineer, it's like communication is very important. You want to illustrate how the very complex ground or very complex like your engineering ideas or very like comprehensive geological informations in one simple graph. So that make a difference between like a well-trained engineers, like outstanding engineers, or like the firm or the team that like get the jobs is the one that able to simple illustrate very complex idea and also complex or comprehensive informations in very elegant like a simple manner. Just like here, we try to represent this ground or this like stress underneath like the ground surface. How is the stress look like when you change with the depth? So for examples here, despite that we also look at like pick out depth. It could be anyone and anything. It could be any depth, but I just pick the depth 10 feet, being consistent with the previous examples. So now, at the same depth, but a different soil profile, we have three different layers. So how do we calculate the total vertical stress? So the total vertical stress is equals to the summations of the, again, is the stress times the, oops, sorry, it's not the stress. So we are looking for the stress. The stress is equals to the unit weight of each layers times the thickness or the depth that you're looking at. So you have however like more layers you want. These examples at this particular depth we go through three layers. So first the first layer we have 1, 2, 3. So the first layer that we have the unit weight of 105 pounds per cubic feet, and then times the thickness, because like we go through the whole layers here. And then the second step, the second layer is just 115 pound per cubic feet. And again, like the depth that we want to get to, it goes through the whole layers. So we multiply the thickness of the second layers and third. Now this one, our interested point didn't go through all the way to the bottoms, but just cut through like guess at a middle point or at some point of it. So we want to go up to 10 feet, which everything stop here. So we're looking at 10 feet. So everything stopped there. And at that depth, the thickness of the third layer we're looking at now is only 2 feet. Because like we know the whole thing is 10, 10 minus 6, 10 minus 6 plus 2. So 10 minus 8, we have 2 feet left. So here is only 2 feet. So we only have 2 feet. So here we calculate up to the point that is 10 feet down from the ground and also 2 feet down from the second layers. So those what we need to calculate the stress. And at the end of the day, if we do our math, we get 1170 PSF, pound per cubic feet square. Sorry, pounds per feet square. So this is our answer. That we look at particular stress, 10 feet down, and what stress is it? This is the total vertical stress. So we shouldn't be satisfied on just finding a number at a point, but we should able to illustrate the whole thing as a stress profile. So again, this is the stress profile. We're looking at the total vertical stress. So and now since we have a layering systems, so it's not a straight line anymore, but like the slope of the line will change with the unit weight, right? So just like the previous one we talked about, if you only have one layer of soils, homogeneous soils, you got a straight line, and the slope of your line is pretty much just the unit weight of your soil. So here now, the first layer pretty much like we get to the point that we should stop here, right? So this is the calculations of the stress for the first layer. So it's 105 times 2, we should get 210. So this is the stress at the first layer, at the 210. And then like we will calculate the stress up to the second layers. So pretty much like you will be this part of calculations. Then if you do the math there,
add up the two terms, then you get 900. And finally, we got our final results at 10 feet that we were looking at. It is 1170. So let's say this is 1170. So if we connect all the dots, then we get something like this. So the drawing may not be exactly according to scale, but you get the idea how to do it. So this is our stress profile for total stress, total vertical stress up to 10 feet. Well, since we just only calculate up to 10 feet, but like, same procedure, you can keep going. So, but anyways, so this is the stress profiles for non-homogeneous soils. Okay, next, let's talk about the vertical effective stress. So we're still under the domain of vertical stress, but now what we look differently now is there's water. There's a water table right there. So we have two choices when there's water table. We can still consider the total stress for particular, like, design reasons that we will cover later, or we should more likely we should look at the effective stress, which we consider the effect of the water. So at this point, like, my requirements for this class is you need to be able to do both. You need to be able to know how to excuse me, calculate total stress and also calculate vertical stress, effective stress. And when you move on to the next class, I see 4, 6, 7. If you choose to, then at that point, then you will learn, or you will like, required to tell, or to you should able at that point you should able to do some design. Then you should able to pick, should you use total stress or effective stress. But at this point, the minimum requirements for this class, you need to know how to do both, such that you get ready for the design, that, like, you can choose like either one of it based on understanding, and you come with a conclusion. So you come with a design that for your class or futures, for your real project. But anyways, now we are doing the vertical effective stress. And the vertical effective stress comes with this framework by Carl Terzaghi, which is the father of geotechnical engineering. So when we get to soil consolidations, we'll talk more about Carl Terzaghi. So he's a very famous at the time of the civil engineering. He is exactly 100 years older than I am. So I guess, like, before the railroad to before the railroad period, you know, um, he is the one who defined the tones of civil engineers. So ASCE also have a book dedicated to his contributions. So and one of his major contributions for us, for civil engineers, is come up with this effective stress concept. So what does it mean is, this equation here, the effective stress is equals to the vertical stress. So all those are vertical stress. So the effective stress will be equals to the total stress, which you know how to calculate already, minus the pore pressure. So this letter U is pore pressure. So like your soil hydraulic class, lecture 3, I remember, the unit weight, the pore pressure is calculated as the unit weight of water times the depth of the water table. So this is the depth of water table. So for example here, let's do a quick examples. To find the effective stress, again the same profile, but now we have a water table at 3 feet down the ground surface. So we want to calculate the not only the total stress, but also want to calculate the vertical effective stress. So the vertical total stress, we have done that already, is equals to 120 pounds per cubic feet times 10 feet. And we get 1,200 pounds per feet square. And the water pressure for these examples will be equals to the unit weight of the water. So unit weight of water is equal to 62.4 pounds per cubic feet, or 9.81 kilonewtons per meter cube. So let's stick with the pressure system here now. So the pore pressure will be equals to unit weight of water, which is 62.4 pound per cubic feet, times the depth of the water table, which means from the locations you are investigating to the surface of the water table, which is like now we are investigating a depth of 10 feet, and then to the location of the groundwater table is right here, is 3 feet down. So the from this pond to this pond, which is 7 feet. So times 7 feet. So with this two, we have 437 psi. And the effective stress will be the difference between the two, will be equals to total vertical stress minus the pore pressure. So you have like 437 subtract from 1,200, then we got 763 pounds per square feet. So that's our answer. Okay, remember, we shouldn't be satisfied on just able to manually calculate 1 point. But as engineers, you want to be the standard one. You want to be much better than a computer. A computer or a simple spreadsheet can do all the calculations that we have just done. But as engineers, we can present, we can tailor make and also present our results based on the project, which means we need to able how to calculate the stress point. So in the exams and also in the homework, I'll ask you to come up with the stress plot. So first, we do our total stress. So when we do the stress plot now, we are not only required to do the total vertical stress. We should able to also do the pore pressure and also the effective stress on the same plot. So first, let's do our total stress, vertical stress. We have the answer, which is like a 1200 at a depth of 10 feet. So we know at this point, it is 1200. So we should, on the x-axis, it should be like the total stress, effective stress, and also the pore pressure. So we try to represent all these three on the same plot. And the total stress is straightforward because now we all have a homogeneous soils. So it will be just a straight line representing the slope of the unit weight. This is 0, so that's the total stress. Next, how about the pore pressure? So the groundwater tables happen here at 3 feet down from the ground surface. And we're looking up to the 10 feet depth. We know that at the depth of 10 feet, or maybe we start from the ground surface. So it was 0 at the beginning. And in this case, we can assume before hitting the groundwater table is 0. So we can do this for undergrad level. For C3660, we can assume the pore pressure of water is equal to 0 when above the groundwater table. So GWT means the groundwater table. So we only can do this for this class. These are simplifications. It's an assumptions. If you really dig into soil mechanics, particular unsaturated soil mechanics, then you will learn more about the energy and also the matrix suctions on the zone that is above the water table. So it's purely graduate level. It can get quite complicated. But for our Geotech 101 class, we assume the water pressure above the groundwater table is 0. So up to the year, we got 0. And we know that at 10 feet, down, we calculate this is 437. So let's assume like a four, well, let's do by eyeball, like 437 is here. If you do on a graph paper, you will have a much or Excel spreadsheet. When you try to plot it out, you will get much like a precise uh, uh, stress plot. But here I just eyeball. So the water, the stress plot representing the water pressure is the blue one here. So the blue one is the water pressure. The black one that we just have just done, this is the total stress, total vertical stress. So we also do one for the effective stress. So this is effective. And it starts from 0 at the beginning. And we know that the effective stress, in fact, is the difference between the black and the blue line, right? Because like the effective stress is equals to the total stress minus the pore pressure. So pretty much like when pore pressure equal to 0, the total stress will be equal to the effective stress. And we also calculate this at the depth of 763. And we got a straight line right there. Again, this is just by eyeball. So with this graph here, with this three like this lines like this is like a bilinear lines, but it highly depends on how many soil stratums you have. Sometimes this can get quite complicated if you have many different soil layers. But anyways, this is my expectations. You know how to plot the stress plot, not only for the total vertical stress, but also can illustrate how the pore pressure and also effective stress change with depth.
Right, let's try another example here. Try another example here. So we have two examples, but let's focus on the one that on the right hand side. So we have two different soil layers here. First, we have 6 meters of fine sands on top of another layer, clay layers over there, and we are particular like interested in locations, which is 8 meters below the ground surface and 2 meters into the second layers. So we at that level, we want to find out the total vertical stress, and also we want to find out the vertical effective stress. So this is what we want to find out. And also we know the groundwater tables is at 4 meters down from the ground surface. So first, we can find the vertical stress first, which is for examples will be equals to the unit weight of the first layer, and always don't forget about the units. And you go through our interested locations is penetrate through the whole like a first layer thickness. So we consider the whole thickness over there, which is 6 meters, and then now get into our second layers. The unit weight is 16.5 kilonewtons per meter cubes, and we are 2 meters into the second layers. So if we do our math, this will be equals to 151 kilopascal. Next, we calculate water pressure. That will be equals to the unit weight of water, which is 9.81 kilonewtons per meter cubes, and the depth of the water table from the groundwater surface to our interested locations will be equals to 4 meters for this case, because we got 2 meters here and here is 2 meters. So this times 4 meters, that will give us approximately about 40 kilopascal. So I don't have a calculator here, so I do like a rough estimations. But if you have a calculator, highly recommend you to figure this out with more precise answers. Then our vertical effective stress will be equals to the difference between the two. And then we do the math to subtract 40 kilopascals from 151 kilopascals. Then we get 111 kilopascals. So that will be our answer to this particular locations, which is 8 meter deep from the ground surface. Okay, now remember, we always not satisfied on just finding a single number, but as engineers, we can tell the full picture, how the stress change with depth. So we also need to find out. I recommend you guys able to do this. You're able to plot out the stress plot. So we're asking you homework, and also we're asking the exams to come up with a stress plot. And on stress plot, on the x-axis, we're representing the vertical effective stress, the total stress, and also the pore pressure. And on the so this time, our unit is kilopascals, and on the y-axis, the unit is the depth in meters. And we know the stress change at the groundwater tables. So this is one locations you want to capture on how the stress being changed, and also add the interface, and also at the final locations that you're looking at. So here is 4 meters down from the ground surface. Is 4 meter down. This is 6 meters, and this is 8 meters. So first, let's start with the total stress. So for the total stress, we know that like the stress change at the interface between layers. So at this point, so for the total stress at 6 meters, so we want, well, let me do it here. So we want to find out the stress, total stress at 6 meters. Will be equals to 19 kilonewtons per meter cubes, and then times the thickness of the soil layers, and that would give you 114 kilopascal. So we know like it starts from 0, and then like I will go to 114 kilopascal. So let's say this is 114, and then we have already, well, so pretty much like the 19 times 6 with this part of the equations that we have already been done. And then like I go 2 more meters down at different soil layers, then we will get us to 151. So this is example, this is 151 kilopascals. And if we connect all the dots, then that will give us the total stress profile. So this is the legends that we have. So the black line is the total vertical stress. Then now let's do the pore pressure. So the pore pressure, it is 0 before we hitting the groundwater tables, which is like 4 meters. Again, we can assume this for this introductory geotech course, but if you move on to graduate study, you will learn that the pore pressure is not 0 before hitting the groundwater table. You will have an unsaturated zone, which tells you actually the pore pressure is negative. And like you will learn more in depth unsaturated soil mechanics when you go beyond this class. But for now, we can assume this is 0, and we know that the water pressure, we have already calculated this, at the depth of 8 meters is equals to 111. So slightly less than 114. So this is 111. Wait there. Oh, sorry. Actually, it's 40. My bad. So the water pressure, we've already calculated that already. So when you go water pressure at the depth of 8 meters, sorry, at the depth of 8 meters is 40 kilopascal. So it's, oops. So it's somewhere here. It's about 50. So 40 is about here. So this is your water pressure. If we connect that, so that give us the water pressure profile for your site. And next, we will calculate the vertical stress. I'll put it on with color red right here. And we know the vertical stress, effective stress is in fact is the total stress minus the pore pressure. So when pore pressure is equal to 0 at the beginning, from our case here, then the effective stress is equal to the total stress. So we follow this line, get to this point. And at at 6 meters again, the total stress is 114, and the pore pressure at that point is equals to the unit weight of water. Now at 6 meters, the water depth is 2 meters. So at 6 meters, the water depth is 2 meters. So this gives us about 20 kilopascals. So if we do our math, our vertical stress will be equals to the total stress minus pore pressure. So that will be equals to 94 kilopascal. So this is 6 meters. So this is about 94 right here, somewhere there. So this is 6 meters. And at 8 meters, we have already calculated already. So the vertical stress is about 111. So slightly less than 114. So we got our final vertical stress here up to 8 meters. And if we connect all the dots, that will give us the vertical effective stress. So here with this, in fact, here with this like a plot over there, including legend, this gives us the stress profile. So it's not only like tell you at one location at a time, but illustrate how all the three stress components, the pore water pressure, the total vertical stress, and effective vertical stress, how three of them change with the depth. Okay, before talk about the horizontal stress, there's another very important concept we need to introduce, which is the P consolidated pressure, P consolidation pressure, P sub P. On some book require maximum pass pressure, sigma pi P. So this particular parameters is related to the topic of stress history. So what is the maximum pass pressure? In fact, it is the maximum effective vertical stress that a particular soil element at certain depth that has sustained in the past. So for example, it's like maybe underneath your house, like imagine like you have soil profiles, and along the soil profiles, what is the maximum loading it has ever been like a loading on the soil, and that particular maximum loading is the maximum pass pressure. And this is very important to recover this piece of information, knowing the maximum pass pressure, because like we will work on the site, we will work on the the soil, and we want to find out this maximum pass pressure, because we know that once we go beyond this like a stress level, then the soil structure, the nature of the soil structure will begin to deform at a different rate, at a much faster rate. So we will concern about the settlements much more. We will concern about the deformations. So the idea is because like soil is a plastic material, so pretty much like if you're loading on the soil, it will form, it will stay there at a particular like a structure So you imagine like a soil, we talk about geological timing, we talk about thousands of years. So the structure of the soils is formed by how much loading it has been like experiencing. So if it has been like stayed there for a long period of time, so pretty much the structure form, the structure of soils. So when we talk about the structure of soils, that would be like the minerals and also the react if a clay, we are concerned more about the clay when it comes to stress history, maybe the reactions between the water and also the minerals, and also how each elements, each ions, how they're interacting with the water molecules, and also between different like particles itself, and give you the structure. And if you're loading on it, you will change the structure, and the loading will change, the structure will change more rapidly when it is experiencing loading that it hasn't been experienced before, a much higher loading that it haven't experienced before. So that's why, like this maximum pass pressure is very important, and we can recover this like a piece of information through our geotechnical laboratory testing, what we call the consolidation test. So one very key concept to remember is soil remember. Oops, soil remembers. So what the soil remember? It remembers the maximum pass pressure that we just talked about. So let's do a quick like a demos on like the picture in the middle is try to demo like what happens where's the maximum pass pressure come from. For example, like this is soil site. To be more precise, maybe I make it up. This is the ECST building. So this is the engineering buildings on campus. So this is today, 2020. So imagine, oh, maybe like maybe not like the ECSD building because you have a structural over there. I don't want to be complicated with structural loading there. Maybe this is the open courtyard. Remember, like within like our between our A wing, C wing, and B wings of ECTS, where like we have an open courtyard where the ASCE canoes and also the ASCE competition teams will work on there. So it's kind of like a free field area. There's like a no structure on top of it. So imagine like that little courtyard. This is the soil profiles of it, and this is 2020. And like if we try to find out the stress like 10 feet down and assume we know the unit weight is 120. So this theoretical stress, effective stress, well, because we don't have water and assume there's no water tables, so the total stress equals to the effective stress equals to the total stress at 10 feet of like a year 2020 would be equals to the unit weight of the soils times the depth. So that would be 1200 pound per cubic square, right? Well, if I'm well, we are learning this, so let's not try. Let's try this way everything. So there'll be unit weight times the depth will be equals to 120 pounds per cubic feet. Uh, Crip times 10 feet down. So give us 1,200 psf. So this is the stress now. But like in the past, we don't know like what kind of like a stress history of this site has ever been experienced. Um, well, we don't know, but like we can make it up. So let's assume our many years ago, there's like some like maybe a small like soil piles or like a little like a small like pile of soils has been like a sitting there for a long times. So let's say this is like a 2000 years ago. So this is year zero. So let's say like this is right at the time that like Jesus Christ was born. So year zero. And like this was exactly 2200 years ago. There's kind of like a little small mountains over there. Maybe another like a 10 feet of soils, the same soils. That was like a sitting there for a long period of times. But throughout the geological times, 2000 years, erosions happens. So it was the soil was gone. But like a 2000 years ago, the effective stress equals to total stress will be equals to, well, again, the same like depth that we are looking at. So let's look at the same elevations. So the same depth that we were at. So this is like a 2200 years ago. The stress will be equals to the new age of soils times the depth, right? But now the depth is like a 20 feet because like there's another 10 feet got like a eroded rate through years. So this is times 20 feet. Then we got the stress in the past. So this is the past pressure is 24 psf. That was the stress that happens 2020 years ago. But now this is all gone and this is the stress we have. But like if we want, if like, but what happens actually happened to our soils is the past history. We are standing now and then looking to the past. We don't know again, like this is what I make up, but like from what I make up, what actually happened to the soil is you have a past pressure that is 2400 psf that was subjected to your soil elements at the depth that we're looking at. So what this like a soil elements we remember is this past pressure. So what happened is the structure of the soils, it retained the loading informations because it was compressed by this much pressure for a long period of time. We don't know, maybe 500 years, maybe 600 years, or through time gradually, it got eroded. So, slowly the stress transform from 2400 to 1200. But what happened is the soil structure. I mean the soil, the clay. You remember this pressure because it was the maximum past pressure that um, he has experienced. So this information is retained on the clay structure. So I keep on saying clay structure. You could remember, imagine, uh, uh, if you use a microscope to look at the clay particles, you will see many like a sheet type kind of layers, um, that like like many pieces of paper. They are cards. They are stacking on top of each other. So the structure of the clay. So this is how the clay look like if you use a microscope. And like the structure here, how these minerals or these like elements or particles they stack up with each other. It is dictated by the stress that it has ever been subjected to. So this structure, remember the 24 PSF. So even though we don't know what happened in the past. This is the past that like we don't know. But like this piece of information is retained on the clay structure, and we can retain by the maximum past pressure. And actually we can recover. We cannot recover like exactly what happens like how tall was the mountains was, like how many like what type of soils was it before, information such that, but we can actually repeat, retreat or recover this piece of information by doing the consolidation test. So when we get to the topic of consolidations, we'll talk more about this. How to use soil odometers performing consolidation tests that we can recover the maximum pass pressure. So that will be kind of like second half of this class. And then we spend a fair amount of time to talk about this, how to find out the maximum pass pressure. But here, the expectations for us is to know, to at least to understand what does it mean by maximum pass pressure, and where is maximum pass pressure come from. We will need this piece of information for the next slides and also for the calculations of horizontal stress. Okay, if you have any questions, I know this could be a little bit abstract, but like if you have any questions, please come to my office hour.
Okay, a little bit more terminology. Another very important term to learn is the OCR, which stands for overly consolidations ratios. So this OCR ratios is defined as the maximum pass pressure divided by the current vertical stress. So go back to our previous examples. So our ECST engineering building courtyard. Remember, at 2020, at current years, current period now, the vertical stress we calculate is 1200. And we managed to recover the maximum pass pressure to be 2400 PSF. So the OCR ratios will be equals to the maximum pass pressure, 2400, divided by the current vertical stress, which is 1200, right there. So the OCR ratios is 2 for our examples here. So this is something that like we make up, right? Remember, like we make up that there was like a mountain right there. We make it up that assume we know like how tall was it, and also we know assume that like how much like soil being evolved right there. And in fact, for this piece of information in practice, in engineering practice, we will find out through our laboratory test results. Which we call the consolidation test. And we talk about this, I think, in lecture 7. If you go back to your syllabus, like, we get to the topic of consolidations, we spent a lot of time. Actually, we just talk about this consolidation test. And if you take your 368, the laboratory class later, we will spend 3 weeks of times to doing this test together, consolidation test. So it's a huge part of very important component in geotechnical engineering, how to recover this information. But we're not there yet. But like at this point, we need to have the concept of what does it mean by maximum pass pressure, and with the maximum pass pressure divided by the current stress, we get this important parameter OCR, overly consolidated ratio, and this is defined by, again, maximum pass pressure divided by the current vertical stress. So knowing this OCR ratio here further help us to define like 3 different type of soils that relate to the stress history. So stress history is very important. It's another learning objective for this lecture number 5. So speaking of stress history for soils, we can characterize it for the soils into 3 categories. First, the first type of soil is overly consolidated soils. So the mathematical definitions of OC soil is the OCR ratios. We just learned how to calculate that. Again, like we have the maximum pass pressure, the information from our consolidation test results developed by the vertical stress. So this OCR, if this is greater than 1, which means the maximum pass pressure is greater than the current stress. So that means like the soils
that have been so that's mean the soil that has been subjected to the effective vertical stress is in the past is more than in excess of the present stress. So that's why you have your OCR greater than one. And why that happens, very likely like the examples that we have done here. In the past, there was like a mountains or like other kind of floating. It could be a structure, and then you got demolished. So the ground is the soil has been experienced like a much higher pressure than the current stress now. And in fact, this is the most soil, common soil in nature, because geological time is long. We talk about like 10,000 or 100,000 of years right there. In the past, very likely, a lot of erosions and a lot of like the earth have a lot of like mobilizations have go through. So very likely, natural soils you will be over consolidated, but it's just a matter of like how much. It's like a two times, three times. Sometimes the OCR ratios can go up to each time. So that will be a heavily consolidated like a soil. Likely consolidated soil could be like 1.5 or 1.2 or like 1.6. Even like if OCR equals 2, we also consider it to be like a likely consolidated soil. So it happens because of the caused by erosions or the change of groundwater table. It can happen too, because either by erosions or by change of groundwater tables, what happens is the change of the vertical effective stress. Whenever there's like an increased vertical effective stress, which means could be water table like a drawdown, right? If the water tables go down, and then like the pore pressure go down. With the pore pressure go down, remember this, right? Effective stress equals total stress minus pore pressure. So if this go down, this will go up. So even without erosions, if there's like a groundwater table drawdowns because of drought or whatever, and then that will end up happens will be an increase of vertical effective stress. So that will be make the soil become overly consolidated too. So and that scenario we have is normally consolidated soils. And that one, mathematical deformation is the OCR is equals to 1. So it happens when your past pressure is exactly equals to your current vertical effective stress. So this is where in the nature, but it could be common during constructions. For very young soil deposit or those either in the field or in the lab, like man-made activities or constructions activities. You have backfill, could be like the slope at the back of your house, or could be a retaining wall, or earth retaining wall, or like kind of like a levees, earth levee, like you put on the soils. You want to bring up the grading, you want to bring up the elevations. So when you put the soils, deposit the soils on your site, that would be like you manually making the soils. And if you well, for example, this this is the ground you want to put on. You put on the field, and this is your mamic materials. And like once you paste it on, the soils will start consolidated. And to a point that vertical stress is equal to the maximum pass pressure, then you have normally consolidated soils. When OCR equal to 1 means the maximum pass pressure is equals to current stress. So the third category is when we have under-consolidated soil, which means the OCR is less than 1. In that case, maximum pass pressure less than current stress. So which means the soil is just like a deposit, or like either by construction activities or geologically.
So you have a landslide. The soil's just like, being like mobilized, you go down by itself. So the slope at the down slope, or like, you by like, well, for example, like, if there's a landslide happens, so this part of soils got scooped down. So the soil here is just like a newly deposit. So this is still like, being fresh, and still under consolidated at that point. So that will be under consolidated. It happens actually it happens quite often in offshore, like, the under the seawater, the marine slope, there's a lot of like new forming soils happening offshore. Or like again, the examples that we look at before, right? The fill material that we paste on. So at time equals 0, once you paste the material, and then like, the soil will consolidate it by itself, and then like the soil is forming, and then that time is underly consolidated. And to upon the times equals to the end of primary consolidations. This is T sub P right there. So this is like a more advanced concept, like the end of consolidations or the end of primary consolidations. So if you don't understand all this, that's okay, because like we will come back to here about consolidations in lecture 6 or 7. The later part of this semester, we spend a lot of time talking about what is primary consolidations. But like, uh, the idea of under consolidated and normally consolidated, they are like similar. So at this point, what I need you to truly understand is this formula. What is OCR? And like, it will be good for you to able to pick up these three concepts. When OCR equal 1, greater than 1, require overly consolidated, means the maximum pass pressure greater than the current vertical effective stress. So if you're not getting too much about the normally consolidated soils and under the consolidated soil, that's okay. We'll come back to it at the later part of the semester. But at least I want you to understand normally consolidated means OCR equal 1, the pass pressure equals to current stress. And under consolidated means the OCR even less than 1, which is very rare. So in the design, many part we will design for overly consolidated, and some scenario we will also design it for normally consolidated. Under consolidated is very rare, unless like you practice in the oil industry, in the where you have offshore a lot of offshore project, the geo platform like maybe in the deep sea, in the Gulf of Mexico's like those projects, then maybe you will come across like many soils still under consolidated. But again, this course key concept, what is overly consolidated ratios, and like what the difference between overly consolidated versus normally consolidated. If you can tell the difference and you truly understand this, I think that would be fair enough for this class. Okay, so for horizontal stresses, so one of the concept here is you need to understand that horizontal stress is something that really hard to directly measure. It's almost impossible for us to able to directly find out or directly calculate what is what actually are the horizontal stress in the field. So the common way to get around it is by making use of the coefficients of lateral earth pressure. This is at rest conditions. So K naught, we make use of a parameter called K naught, is the arrest lateral earth pressure. And the K naught is defined, is a kind of like a soil properties. Um, there's like a multiple ways to try to estimate the K naught, but like to understand this, you need to realize K naught is a soil properties. So K naught for sand, K naught for clay, or K naught for gravel, or more like specifically like a K naught at Los Angeles sand, or versus K naught at Tokyo sand, or like the London clay versus the Potomac clay at Washington D.C. and also maybe like San Francisco Bay Mud, the K naught or different values. And if you like a practice in the area long enough, then this number should be on top of your head. What kind of K naught value should you be for this for the design project you're working on? So K naught now K naught is something that you can estimate, and the vertical effective stress is something that you can calculate based on the unit weight of the soils too, because unit weight of soils is simple, cost effective, able to find out as long as you know the unit weight, which means like you know the phase calculations, you know the volumes, you know the weight of the soils you collect from the field, then you can find out the unit weight. You know the unit weight and you know the depth that you're looking at, then you can find out the vertical effective stress. Plus, if you have some centimeters like readings, you know the water tables like from the field, then you can find out the effective vertical stress. So vertical effective stress, K naught, then you can find out the effective horizontal stress. So that's the plan on how to find out the horizontal stress in practice. Again, one more time, because like horizontal stress, this number is almost impossible for us to directly quantify. So that's why we make use of the K naught and also we make use of the vertical stress. So we talk about more about this uh, the procedure wise how to find out the horizontal stresses, and at the end we'll do examples too. So the K naught is at rest lateral earth pressure. What does it mean? At rest means, so if you want to find out the stress of a soil element in the ground, and at rest means no lateral movements, no lateral deformations. So that's why the vertical stress here and also the horizontal stress here. So this K naught conditions is work in a way that we assume there's no lateral movement. So that's why we call it at rest. The soils at the lateral direction is at rest. It's just okay to do, or actually like we assume all the deformations only happens vertically. So it's a 1D deformations, one-dimensional deformations problems, which means like when we're loading on the ground, all these settlements, all the deformations only happen in the vertical directions. Horizontal directions, there's no movement. So if you take a structural cause, it's kind of like a roll bearing that you're dealing with. So it kind of like a restricted in the lateral directions, but forcing all the deformations only go vertically. And with that, like assumptions being a rest, then this cannot how this is defined. For the case of design that when you have a geostructure, maybe it's kind of like a retaining wall. If the retaining wall, so so for example, if you have a retaining wall, this is backfill of soil, and this is your retaining wall. If this retaining wall moving either like away from the soils or moving into the soils, so at that times you're not at rest conditions. Pretty much you are at active or passive conditions. So this will be further because we realize that uh, instead of just like at rest conditions, you can also still in active and passive conditions, K and KP. But this will be taught in will be introduced in C467. So when it's zero, geotech design number one. So if you want to learn more about this, like further study in this topic, this class, like we need to keep a cap because like we only have one semester. Sometimes it's only 10 weeks, so we have very limited time, so we cannot go too far
But like at this point, we need to understand what does it mean by arrest conditions. Means 1D deformations. All deformations only happen in the vertical directions, and horizontally is kind of like a restrained. So with that, because think about it, if so, we're talking about the horizontal stress right here. So if I saw an element here, we are talking about this horizontal stress. So with with the like a boundaries able to move or not able to move, you make a huge difference on the magnitudes of this horizontal stress. So that's why we need to have this definitions very clear at the beginning. We only deal with at rest conditions for this class. Active, passive, leave it to the senior level class. So at rest conditions, laterally, nothing is moving. So if this is a rigid response, what kind of like horizontal stress we are getting? So that's what we try to calculate it here. So I'll mention like the K naught values is something that like is so type dependent. So rule of thumb, very rough estimations. It depends on the stress history as well. So if you have a normally consolidated soils, so that's why like in the previous slide we spent so much times on talk about what the difference between overly consolidated and normally consolidated. Now like you come back to help us to find the K naughts. So for normally consolidated soil, the K naught values is ballpark is about zero point 0.5 plus or minus -1, plus or minus zero point 0.1. For overly consolidated soils, then like you need this formula. So this formula one more times is K naught and overly consolidated like conditions is equals to K naught NC consolidated. So this number is about zero point 0.5 plus or minus 0.1, as we mentioned before, equals to this parameters times the OCR values. So the OCR value, we talked about this before, is the overly consolidated ratios, is this formula right here. You relate to the maximum pass pressure divided by the current vertical stress equals to OCR to power m. So this is a curve fitting parameters. So this whole formulations are purely empirical. It's nothing like a theoretical. So pretty much like it's empirical like correlations that people developed based on many data points or K history. Uh, so they develop like a database and then they come up with these correlations. So this is kind of like a curve feeding parameters. So this M here is a curve feeding parameters. Depends on the soil types. So if you have, and also this number is about zero point 0.4. So if you have like again, like London clay versus San Francisco bay mud, like maybe like a Tokyo sand versus like a lavada sand, you would have very different M values. Well, maybe 0.38 versus 0.45, those kind of range. And you better like, for if you have very like expensive project, you better like conduct all the lab testing and field testing to find out the site-specific M parameters and also the K naught NC parameters. But this is the basic framework to find out the K naught OC conditions. Well, in generals, the K naught and also therefore the horizontal stress is very hard to precisely to characterize. It could be $1 million type of problems for people to figure this out. So, and in the past like a couple of decades, many research effort has been expand on the subject, and we are still working state of the art. We are still keep like working on to improve how to do this better. Because you imagine that this could be a very expensive geotech problems, even though just off by like maybe like a few percent uh, of K naught values, like for examples like 0.0 a 5 versus like a 0.047. We just talk about like 6% of difference over there, but end up you could be uh end up it could be like a very different horizontal stress that you will come out. And the horizontal stress, because again, like if you go deep into the ground, for example, like the metro project is going on right now, the downtown, for example, you need to go down 300 feet deep to the ground to build the metro stations. And like the deeper you go, the horizontal stress will be go up by exponentially. And end up, what does it mean? It means like the materials or the difficulties that you need to go down to build the, like a concrete wall to withstand all the horizontal stress adding on the ground. So if you're off a couple percent of a very large numbers, there's a lot of money goes in. So it could be becomes like a millions or even billion, um, type of amount of money of problems that come up with finding the horizontal stress. Okay, Okay, horizontal stresses, how to calculate it. So I give you some procedure. So like, previously I talked about the concept of K naught. Now, this slide is so to demonstrate, to show you the step-by-step procedure on how to find out the horizontal stresses. Um, First, you what we do is we find the vertical total stress and pore pressure first, and then find the uh, vertical effective stress, just like what we have been doing. Next, you need to know the maximum pass pressure, and then like you estimate the K naught and C, normally consolidated like our values. And I K naught like an NC will be about zero point 0.5. So I give you this, so this procedure number 3 here, I give you this table here to give you some like a ballpark numbers. So if you have a sand, then you would choose the range over there, then sand. Or if you this is like a low PI, so PI stand for the plasticity index, um, so this is the PI, and we talk about this in lecture 2, the plasticity index. Remember that when we do the soil classifications, we talk about this. So if it is a low PI versus high PI clay, then you have different numbers. So in the homework, I need to make you the call. You guys need to figure this out. The homework will tell you this is a sand, or maybe it will tell you it's a dense sands. Based on the unit weight, you can estimate this is a dense sands, and then like if you know a dense and you need to pick up values from there. So this is kind of like really like a practice related. Geotech, you need to handle a lot of uncertainty, and the good engineers is the one that able to make the engineering judgments more precise. So like you need to make a call. If you believe it's a point 0.4, then you can use point 0.4, but you just need to explain uh, how professional ways that like convince people, or you have the faith, like you have the enough experience to make the call. So the more you understand geotech, or the more understand like truly understand like how things work, and also you will take a couple years to build up this kind of like experience to able to have those engineering judgments. It took me like a few years to get there after like practicing in the field. So now, like when I see like all the geotech informations, if I know the density, if I know these both counts and stuff, and all the geotechnical informations, then I can make the call on should I use point 0.4 or point 0.5, 0.45. Given that, like I know there's a dense sense, you know, uh, could be like even point 0.2 or point 0.3. So there's a lot of engineering judgments over there. In the homework, I want you to give a try, and then as long as you defend yourself like in a reasonable way, I will give you full credit. So if when you get to that point when you do your homework, I highly encourage you come to see me in my office hour, and I will walk you through like how to pick up the values. I think that's the best way for you for all of us to learn, by talking to me, I share my engineering judgments, and also I can share my that's the best chance to share my experience with you, how to make the engine judgments. So I highly encourage you do advantage while you're still at school. You can you are you are entitled to talk to me, like or use my consultations. If you after graduate, like you need to either like do on your own, or like you seek help from your boss or small senior personnel in your office, or like you need to pay for a consultant like me, to give you some insight on which numbers to pick on how to approach the problems. So highly encourage you do come to my office hour, and then like if you have any questions, especially working on homework that involve engineering judgments. So the third part is to pick those like K naught values. First, you will estimate uh, the normally consolidated like K naught values. Then if this is NC soils, you stop there. But if this is overly consolidated soils, then you need to go one more step ahead. You need to, after you pick the normally consolidated value, then based on that, so you pick the number properly from this table, and then plug it back, and then you will find, also you calculate the OCR values and the find the FM values. So either like you do a lab testing to get the AMP, so that would be too advanced. Like we talk about how to in the lab how to characterize this M value in the lab. But like very likely for this course, like for this Geotech 366, I will give you the M value, so don't worry about it. It's a soil properties. So you know the OCR, you know the M, and you know the K naught NC, then you will find out the K naught OC, the K naught values for overly consolidated state. So after like you know the keynote the keynote values. So this after you know the keynote values. So the keynote value here is from step number 3, and also like your vertical effective stress from step number 2. Then you can find out the horizontal effective stress. This is very important. Realize that this K naught values, this K naught is in effective stress space is equals to the horizontal stress divided by the vertical stress, effective stress. This is effective stress space. It's not equals to the total stress. This is wrong. Don't do this. I've seen enough like engineers like get in troubles because of this. Sometimes maybe teachers forget about it, or like they didn't learn it correctly at the first point. This is only in effective stress space. Don't do this. This will get you in trouble. Don't do this. This is not in total stress space. This is on effective stress space. So that's why you will always find your effective horizontal stress first through the K naught, because the K naught is in effective stress space. Then after you find uh, uh, the effective horizontal stress, then the total stress will be the effective stress plus the pore pressure. So this is from step number 6. And then you can find the pore pressure again. So remember, like the Tosaki theory tell us the effective stress is equals to the total stress. Oops, sorry, doesn't mean to put the directions over there. So the effective stress is equals to total stress minus the pore pressure. Therefore, the total stress will be equals to the effective stress plus the pore pressure. So this is how we calculate the total horizontal stress. So you would take like go through this procedure in order to find the horizontal stress. Vertical stress, straightforward through the unit weight. Horizontal stress, you need to understand how to make use of the K naught, and also make sure you remember this. K naught is for effective stress space, it's not for total stress space.
Okay, last but not least, let's do an examples here. Let's do examples. This is a real life design problems, which you need to find out the stress for tunnel design. So, for examples, like this is a tunnel openings, the tunnel boring machines that mine through. So if you want to understand how the TBMs, the tunnel boring machines, is working, you can go to Canfax. On the supporting documents, I put on some clips to demonstrate from the Colorado School of Mines, which is I think is the best program when it comes to the topics of tunneling. They have give you some very good like videos to show you or some like a short clips to tell you how the tunnel boring machines work. But anyways, um, so this is a design for a tunnel, and for the tunnel, there's some terminology like at the top of the tunnels we call it the tunnel quang, and at the center line of the tunnel, so this is the TBM machines try to advance in this directions, and along to the center part of the mining directions, this is the spring line, and at the front, so there's all the mining's happening here. It's like there's a lot of like uh, uh, turning and then like minings at the tunnel phase to try to like let the TBA machines to advance in this directions. So anyways, like uh the where typical is like for tunnel design, we need to find out the effective stress vertical effective stress at the tunnel quang, because this is the kind of like the hot zone to carry all the vertical loading. So we want to find out both for the constructions and also for the long-term effects, because the tunnels after you mine it, you put all the shotcrete all the wall to put up over there is supposed to last 100 or 200 years. Like so there's a long-term effects, and during the mining progress, there's a short-term like effects. So when you think of those long-term effects and also the short-term effects, that is the point that you need to think of whether should this be a total stress analysis or effective stress analysis, as we talk about at the beginning of this lecture. So all this like total stress versus effective stress, long term, short terms like design considerations. You take experience and take times to build up your knowledge to make the call. So I don't expect you to know everything, but if you want to discuss about this, I'm very excited to share with you or to chat with you my experience, because I did work in the tunneling field after my master degree for about a little more than 2 years, particularly on a very well-known project at Washington D.C. at the time. So I do have some experience in tunneling field. If you want to discuss more about the design and everything, feel free to come to my office hour. But keep it simple for this class. We want to find out the vertical effective stress at the tunnel quang, and also we want to find out the total horizontal stress at the midpoint uh, of the tunnel face at the spring line. So that's what we want to find out. We want to find out the vertical effective stress and also the total horizontal stress at these two particular locations. So this is the tunnel again, the tunnel here working on. And the tunnel is on geological profiles, and this geological profile is exactly the geological formations of Los Angeles. So I take this out from a real project, the early Metro's like a Purple Line extension project. So based on Los Angeles soils. So this is the geological setting for areas geology, where we have the San Pedro formations on top of the bedrock, and on top of that is the liquid formations, and on top of that is alluvial deposit, and up above that is the artificial field. So all this is geological like formations, and if you want to practice in Los Angeles, at some point of career, you need to know this well. So the liquid formation is a good mining material. It's not too super hard like a rock. It's not like something so too soft like alluvial, like the young alluvial deposit. So something too hard or something too short or too soft is very hard to mine. It's very expensive to mine through. I put it this way. So most economical way, is just go through the liquid formation. So that's why when you mine on the metros projects, usually you will go down in the elevations that to the liquid form. Not more of them, but most of them is in the liquid formations, which is deep enough to stay away from there may be some like foundations you may go through, or maybe some utility lines that you may go through on tops. But like also very economical mining material because not too hard, not too soft to mine through. So now we have the kind of like geological profile. We know all uh, uh, the length and also the thickness of each layers. Then we want to find out the vertical stress at the crown, right? We talk about this. So we want to find out the vertical stress at the crown right here. And also we want to find out the total stress or total horizontal stress at the center of the tunnel face. So those two locations are the one that we want to find out the stresses. So so let's start with the vertical stress, which is much more straightforward. So we have been doing this. So you should be at this point you should be get comfortable on how to find out the vertical stress. Um, so first at the tunnel crown, I'm going to find out the effective vertical stress. So we find out the total stress first, total vertical stress first. So first we have the artificial fields, which have a unit weight of 124 pound per cubic feet times 5 feet, and then plus the second layers, which is 115 pound per cubic feet times 30 feet, plus the final layers, which is the liquid formations, which is 1.7 pound per cubic feet, and then times the thickness now to the corner crown is 11.5 feet. So after we let me use red. So let me use red, and after we do the math, this is equals to 5,415 psf. And we assume the water table is at the ground surface. Now we calculate pore pressure, which is equals to unit weight of water, 62.4 pound per cubic feet, times the thickness. So it will be 5 plus 30 plus 11.5. So we talk about from this point to this point. Those are in feet, and the water pressure equals to 2910.6 pound per feet square. And when we do our math here, the effective stress will be equals to the total stress minus the pore pressure. So the difference between these two will give you 25 and 13.9 psf. So we solve our first problems. First, we find the vertical stress at the tunnel crown. Second, it asks for the horizontal stress, total horizontal stress, not the effective stress. So the total horizontal stress at the tunnel face. So we try to find this. I realize that now the elevation changed it because originally we were looking at like the tunnel crown, and now we are looking at the center of the tunnel face. So we go a little bit deeper now. So we need to recalculate everything. So we will find out the stress based on this procedure, and this procedure at the beginning we need to find the vertical stresses first. And now the vertical stresses need to be updated because you're not at the locations of the crown. You're at the locations of the center of the spring line. So so the result. So first we find out the total stress again. Oops. The V equals to 124 per cubic feet. So you realize when I do all these calculations, so I always put down the units. So no matter like how many times I've done this, I will keep doing this. So all the units, just because like I also want to show off to tell people or tell like my my readers could be like someone reviewing my calculations at professional levels. Uh, I want to show off to them how careful I am as an engineer, and it helps you to if you saw all the units, you will help yourself to eliminate any like errors that you may able to catch. So always put down all the units, and also it helps you to see like what kind of units being canceled out and see whether it makes sense to you. And this is about like 6644 PSF. So now we go a little bit deeper. So that's why the stress we're getting will be higher than previous one you get. And also we need to update the pore pressure. So unit weight of water times the new depth. So you will be 5 plus 30 and then plus 22 feet. So now we also get the pore pressure, which is 3556 PSF for this one. And we do our math. So the vertical stress, the effective stress will be total stress minus the pore pressure. So the difference between the two here will give us 3087 PSF. So according to this procedure, the the third step is we need to know the maximum pass pressure. It's supposed to be something that like we cover from the laboratory test. So in practice, what people will do is they will collect soil samples at the elevations, ideally at the elevations that like the tunnel will go through. So at that particular locations, you get the soil samples and you ship it back to the lab. And from the lab results, you will conduct a consolidation test, and the consolidation test will come back to tell you what is the maximum pass pressure. So for this case, the maximum pass pressure is 6,000 PSF. So it's something that's supposed to given to you, or when you're practicing, it's something that you need to pay for the for the clients. You pay for the clients, or you convince your clients to spend the money to collect soil samples and also do the lab testing, budget the lab testing, and then come back to your office as a test results. So now you know the maximum pass pressure for the locations that you're investigating. What kind of like a number is it? For this case, it is 6,000 PSF. And remember, like we also need another soil parameters, which is the M values right there. So the M values always come back as a lab testing. Let's assume this is 0.4. So we have final the soil parameters of a maximum pass pressure and also the M values. Those are soil properties that like should be given to you like for exams or homework, but like in practice there's something that there's some informations that pretty much you obtain from the lab. So you will be representing the clients, well, first of all convince your clients to pay for the budget to go get us all samples and ship to the lab, and uh, uh, then the lab will return out give you back a lab report, and the report will tell you uh, the maximum pass pressure and the M values, which like this case like is given here. So the next steps we need to work on,
well, according to our like procedure, now we have step number 4. Then we need to find out the K naught values. First, find the K naught and C values. And so the K naught and C values you can baseline from these tables, and it first like based on what type of material is it. This is a sand materials we're working on, and the density of this material is 117. So for sand, so dense like rule of thumb is about being dense configurations is about 125 to 140, or like to be at the safe end, so say 130. So 130 to 140 pound per cubic feet cubes. And for being loose, it's about 110 to 120 pound per cubic feet. In our case, we are 117, so pretty much we belongs to the loose categories right here. So for the loose sand, it's between 0.55 to 0.6. So I would recommend like use the Kano NC values for this case to 0.575. So you take some judgments to make up this number, and like through like experience, and also through like the more you know about geotech, and the more experience you have, like you will be easier for you to make a judgment call. I would say making this call will be the most difficult part in the analysis. So now is well this case you've like for exams homework problems where likely are given to you the values. I think the homework I asked you to give a try to base to to estimate the keynote values. So homework I give you a chance to for yourself like assume you have like much more time than exams. I'd ask you to try to think about what kind of keynote values you should use. And if you have any questions, please come see me during my office hour. In exams, for very sure I will give you the keynote numbers. So don't worry about that. So you have the keynote NC now, and next you need to check whether you need the keynote OC numbers, and that depends on the OCR values. The OCR values. And the OCR is calculated by the maximum pass pressure divided by the current's vertical effective stress. And the maximum pass pressure, given to you is 6,000 psf. And the current effective stress we calculate is 3,087 psf. The unit cancel out. And this is about 2, which is greater than 1. So if like OCR values is greater than 1, so from what we have learned previously, this is overly consolidated soil, because like the OCR is greater than 1. So if we know this is an overly consolidated soils, then we do need the K0 OC number. If it's NC, the normally consolidated soil, then we check out the number from this table. There will be sufficient. But for overly consolidated soil, we need the use another formulas to calculate the parameters right there. This equals to K naught NC times the OCR to power M. And the K naught NC is 0.575. We have found that. And OCR, we have already like calculate that. So this is 1.94. So this is 1.94 right here. And the power M, which is 0.4. And we do these calculations. We find out K naught overly consolidated state is equals to 0.75. So after we find out this K naught NC, then we can find out the effective horizontal stress. So even the problem, again, even the problem asks you the total stress, but we need to always start from the effective stress in the horizontal direction first. So that will be equals to K naught times the vertical stress. So it will be equals to 0.75 times the vertical stress. Again, we have calculated that, which is here, which is 3087 pound per feet square. And we do these calculations. Effective horizontal stress is 2312 psi. And remember, what are we being asked? We ask the total stress, not the effective stress. So what we need to do next, finally, is so the horizontal stress will be equals to the effective stress plus the pore pressure. The effective stress, we just calculated that, and the water pressure, we have done that at the beginning, is 3556, 3556 psi. Your math, finally, we calculate the total horizontal stress at the tunnel face is 5,868 pound per square feet. So always box your final answer. Remember, we talk about this. If we do something like this, this is absolutely wrong. Don't make this mistake. So if you have done this, if you plug in the total horizontal stress right there, sorry, the total vertical stress right there, which is this number here, 5415 or 5416. Sorry, the total stress right here. The total vertical stress is 6644. If you plug in this number, 6644, you will get a different answer at the horizontal stress. And this is not equal to that. And this is wrong. Don't do that. And in fact, you're underestimating the horizontal stress compared to the true one, which could be a dangerous thing, which means your design is misleading. You're thinking the stress is less than it's supposed to be, so you're very dangerous, like at the construction phase. All right, so that's with the end of this examples, I conclude lecture 5. So again, stress calculations is the fundamental of fundamentals. So please make sure you feel comfortable on all these calculations, and be expect that like you will see this type of questions over and over again in exams, homework, and also through your career. So if you need any help, please come see me during office hour. Thank you. Bye bye.